Hey, what's up guys? In this video we're going to be talking about how to control a ton of RGB LEDs. What we have set up here is an Arduino in a standalone configuration just on the breadboard. It's the same as the Arduino board, just all those parts put on a breadboard. Controlling two of these really cool chips, these TLC5940 chips. And those are 16 channel PWM output chips designed for LEDs actually. So there's 16 channels a piece, and we've got two of them daisy chained together. You can just keep daisy chaining these to control a ton of LEDs. Let's see. The circuit itself is pretty straightforward. It's pretty easy to set up. There's no real circuitry, really. It's just going from pin to pin. You set. What's cool about these chips too is that they're constant current LED drivers, so they will sync a constant current without the need for a current limiting resistor. So it handles all of that by an external current reference resistor setting here. In fact, let's just get that out of the way. You know what? Maybe we need to talk about RGB LEDs here for a second and why they're so cool. I don't know if this is coming out real well on the camera because it's probably so bright that it's just drowning all the light out. But I'm going to diffuse the RGB LED with this foam here, and I'm going to load up a test code that runs some animations, which I'll have available to as a link down below in the description. Alright, so it's loading this up, and what this animation does is it randomly creates mixtures of colors from the RGBs and drives them at different PWMs, and it goes from left to right, fading everything on and off. So it's fading into the colors. It's pretty much your Knight Rider LED thing display on steroids. And I doubt this looks really that cool on camera, but right here in this room, when all the lights are out, it glows the entire room, and it just fills the whole room with like a cool fading color look. It's awesome. Okay. So like I said, these are RGB LEDs, meaning that each LED has a red, a blue, and a green LED. I'm going to go back to the lamp test to show that. And you drive these LEDs with PWM, and by changing how much red, blue, and green you put on the LED, that changes the color. Okay? And I'm using this foam so that you can diffuse the color, so it kind of mixes things together for you. Otherwise, you can actually see the individual RGB in each of the LEDs, and then it kind of loses that cool effect. Okay, so let's talk a little bit about LEDs here. Got the whiteboard out. Okay, I don't want to spend too much time on this, but probably be a good idea. So when you buy one of these LEDs, you've got like 4 leads on them, and it could be either a common anode or a common cathode, and usually one of the leads will be longer. That's the common of the LEDs. And it'll, like, if you look closely, it's got the biggest meat inside the LED, while the other ones kind of are like little specks in there. So if you follow it up, if you can even see inside the LED, the ones I got are not the diffused lens. And if you do buy these, it'd probably be a good idea to get the diffused lens, which is kind of looks like it's been like smoked, so you can't really see the guts. It's kind of has like an iced look to it. That way it'll mix all the colors nicely, so that when you look at the LED, if you made like orange from driving the pins in the right way, then it'll actually look orange and not, some mixture of, red and green and blue. Okay, anyway, I'm probably sounding like an idiot right now. But anyway, common cathode. Let's talk about common cathode real quick here. Common cathode is when that's definitely not common cathode. Where's my eraser? So you got your 3 LEDs here. Okay, and they're all in one package. The anode pins of each of the LEDs are broken out but the cathodes are all tied together. Okay, so if you wanted to control this, if you wanted to create different colors using this, you would ground that one pin, the cathode, hook up your current limiting resistors, and then you would drive this. So if you put 5 volts on each one of these pins, you would get white, basically, I guess, because you've got equal amounts of red, green, and blue. So one way to create different colors would be to put different voltages here. Okay, that's not very easy to do with an Arduino because you only have 5 volts or you don't have 5 volts. You could change the resistor values here. That would give it to you, but you can't change that on the fly or very fast at all. So what you do is you use PWM, which is just square waves, basically. Okay, so if a perfect square wave like that applied to this, and let's say it's just repeating, and it's equal amounts of on time and off time, that would give you a duty cycle of 50%. So that means that the on time over the total time, that ratio is 50%. And you should get 50% brightness out of that LED. Now, what's cool about PWM is that you can change how much of the on time you have versus the total time. So in a case like this, let's just say that's like 90%, then that would change the brightness back up to like 90%. So, because if the pin is always on, that's 100% brightness. Okay. Now the library that's built into the Arduino code when you're writing this, you could do it, and you'll notice when you're looking at the board, some of the silk screen will actually say PWM. And to do the PWM, you use the function analog write. Okay, and it's a value from 0 to 255. So when you write 255, you get 100% on. If you write 0, it's 100% off. So if you write something like 127 to it, let's just say you write like 127 to this thing, that gives you that nice perfect 50% square wave. In fact, if you looked at it using a scope, you would see that perfect square wave. And we'll get into that here in a second because it is pretty cool. Okay, so to change what the overall color of the LED is pretty simple then. So you change the brightness, so you could make this like 20% on to the one pin, then maybe you want this to be 90%. Something like that. So you write these different PWM values, and that'll change your overall brightness. So you've got one LED which takes up 3 of your Arduino pins. Well, that's where the TLC5940 comes in, because it's got 16 channels. So right here I've got 10 RGB LEDs, which requires 30 pins. Okay, you don't have 30 PWM pins on the Arduino. You don't even have 30 pins. So the way you control this is using the TLC5940. And I guess we could get into like some of the theory of how that puppy works. Basically, this chip is not that smart. It's just a really advanced counter. So what you do is you got 16 channels. I don't know a good way to represent this, but actually it starts at 0 to 15. And I've got 2 of them daisy chained together, so it just keeps going. So I actually have 32 channels total. So that's 32 pins. Okay, and I have 10 LEDs here, which would means I need 30 pins. So I'm not using 2 of the 32 channels. But what you do basically with this chip is you give it a value. Now, you remember the Arduino library has a resolution of from 0 to 255. That's the PWM output. These puppies have a resolution from 0 to 4096. So that's, or 4095, sorry. So that's 12 bits of resolution. So we went from 8 bits to 12 bits. Thought I heard a buzzing. Okay, anyways. Sorry, they're paving my parking lot here. Making all kinds of noise. Okay, so anyways, what you do with this chip, though, is you give each channel a value from 0 to 4095. So let's just give channel 0 a value of 4095. We'll give this one like 2048. 2048 would be 50% on. for like channel 1. And you give this for each channel, and then what you have to do then is you give it a grayscale clock, which has to be a fast clock. Like, I'm talking, you remember the Arduino library here actually has a frequency. You know, we have that square wave. The frequency of that is like 40 or like 490 hertz. So it's pretty slow. We're going to actually clock this thing in at 8 megahertz. Okay. But wait, that's not the switching frequency of this. That's the frequency. So if we feed in that, I got to slow down a little bit here. So if we feed in that grayscale clock at 8 megahertz, that's connected from the Arduino to this GS clock pin. What the device does, what the TLC5940 does, is it clocks up from 0 to 4095. It has an internal counter, so every time it gets a pulse from this 8 megahertz thing, it goes from 0, 1, 2, 3, 4, all the way to 4095, and then it resets. Okay, or it doesn't reset automatically. You have to tell it to reset, otherwise it just sits there and locks up. So what it'll do is it'll keep clocking all the way to 4095. Okay, so until you have basically 4,096 pulses on this. And what it does is it remembers where it's at. So it knows that this is 0, 1, 2, 3. And it goes, it might even start at 1, I don't know. Because I guess if you had 0, if you wrote a 0 to it, it would be off. So what's the point? But what it does is each one of these channels compares itself to the value of the overall counter that you're counting it in at 8 megahertz, okay? So what it's doing is, if you had 4095, let's take 2048. So if it looked at channel 1, and it's continuously looking at all these channels, by the way, what it does though is it keeps the pin on until the counter reaches 2048, and then it turns it off. Okay? Until the next cycle, then it turns it back on at 0, turns it off at 2048. So that's how you generate your PWM. So at 4095, that would keep that pin all the way on until 4095, which would just not even turn it off, really. Okay, so any value in there, like I counted to 3 here. So if you wrote one of the channels to 3, it would stay on and then drop off right there. So you've got 16 channels doing this, and that's your PWM. But if we're clocking it in at 8 megahertz, that means we're getting a count of every at 8 megahertz, which I think is 125 nanoseconds. If that's right, divided by, I gotta do 1 divided by 8 E6. There we go. Yeah, 125 nanoseconds is every pulse. Okay, so what I'm actually getting here is 125 nanoseconds times 4096. So it goes through here, but it takes 125 nanoseconds times 4096 to get through one entire period of a PWM cycle. So that times 4096 gives me 512 microseconds. So to get from here to here is 512 microseconds. 1 divided by that now will give me my switching frequency, which is 1.95 kilohertz. Okay, so that's pretty good. So I'm getting about 1.95 kilohertz switching frequency, which is a lot better than the Arduino analog write, which does it at about 490 hertz. Okay, so that's how this puppy works. When it reaches the end, you have to do some tricky things with a blank pin, and we'll get into that. Because what happens as soon as it reaches the end here of the cycle, you have to pulse a pin, a blank pin it's called. So it blanks all the outputs, and then that's what reads in the new data. So meanwhile, while this is happening, while it's counting, you should be clocking in your new data. Okay, and we use the SPI protocol. And then as soon as it ends, that's when you clock in your brand new data for the next cycle. Okay, so the best refresh rate you're going to get here is 512 microseconds of update, which I can't even get that. So Okay, so let's take a look here. That's a little bit on that, but one thing that I think people hate about this device is that you can only use a certain kind of RGB LED. You have to use a common anode type RGB LED. And yeah, there's some workarounds with it, but it would be pretty painful to use a common cathode. You could get away with it, but it would be painful. So if you look at the data sheet for this thing, it shows the output circuit. So if this is the output pin, it shows that it looks something like this. And this would be tied to ground. Okay, so right away you can see, and then this is actually the PWM controller. And it's a little bit more than that because this thing current limits as well for you. So it allows you to max out your current at like whatever you set using an external resistor on the IREF pin. I think I'm using 2K on that. We'll get to what that means here in a second. Okay, so right away from this, you can tell that the device can only ground. Okay, it cannot source power. And that's why, so the path is from here to here. So it's switching this transistor on and off, but it can only ground, which is why when you have your, let me just draw these guys real quick, one of these LEDs, which is why when you have your common anode RGB LED, well, you tie this directly to 5 volts, it can only be common anode. Okay, so it grounds the pin through here. It cannot be common cathode because this cannot source the power for the 3 anodes. It can only sink power or sink current, okay? So that's why you can only use common anode LEDs for this. Did I say common? Yeah, common anode. All right, IREF pin, real quick. I just want to show you what that's all about because I'm not going to do a schematic for this. All right, Imax gives you a nice little formula here is equal to VIREF, which is 1.24 divided by your R. So this is the value of the resistance you're going to put on this IREF pin. There's a pin for IREF. And you connect a resistor here to ground. Okay, and you can, what this does for you though is, you know, in this circuit you don't need current limiting resistors for any of the LEDs. It'll actually it'll use constant current sinking, so you don't need to, you can set this current so it'll never go beyond that. So you put this resistor here on this IREF pin, and all of the LEDs will limit to a current set by this equation here. So if you wanted your max to be like 20 milliamps, then you just solve for R. In my case, I use 1.24 divided by 2K, which gives me, wait a second, do I have that right? 1.24, oh, there's one little missing part here. Times 31.5, and this is right out of the data sheet. So I'm going to go 1.24 times 31.5 divided by 2. Okay. So yeah, I'm going to write around 19.53 milliamps. So 20 milliamps with 2K. And that's another thing about this chip. You got to realize that all of these channels, you got 32 channels here, and if you put them all on at 20 milliamps, there's a good chance you're going to blow up something. I mean, you can't use the Arduino to actually source the power for all of these, because you have to realize that all that current needs to come from somewhere. So if you did put them all on, let me just see what 20 milliamps times, well, I have actually 32 channels essentially. So that's like 640 milliamps. So you would blow out your USB driver or your USB port here. I think that limits current to 500 milliamps. And the Arduino definitely cannot handle that, I don't believe. So you need to, when you connect this, all of your anodes, your common anode pins should be sourced from some external source somewhere. And you're sinking all of that current into the TLC5940, so it may get hot. And there's some power dissipation calculations you can go through. But that's only the case if they're all on. And you are using PWM, so technically you're not always full on. You know, you're somewhere in the middle there. Okay, so that's that. Now I just want to go through this bad boy pin by pin, and then trust me, we have to talk about the code, which is going to take a while. I told you this is going to be a long video. Alright, so we talked about this blank pin. What you do here, the blank pin on the chip, and we're going to go through these one by one. So blank pin, the output here, you want to pull it high to 5 volts if you're using 5 volts, and then from that to your Arduino, and we'll talk about which pin on the Arduino when we get into the code. The reason you want to pull this high is that when you pull it high, when this pin is high, it pulls all of the channels low, so it doesn't, it actually, the reason you pull it high is so when you're booting up the Arduino, all of the LEDs stay low. Okay. And the way this pin works, I actually have to go to the timing diagram for this. We pull this pin high at the end of one of those 4096 cycles, just for a second. We pull this pin high, and then we put it low, and then it restarts. That's it. It resets the counter of that 4096. If we didn't do this, then we wouldn't have that nice perfect square wave or switching frequency of 1.95 kilohertz. So we have to pull it high, resets the counter, resets the cycle. Okay. Maybe I won't go through these pin by pin. There's the V, because the other pins, the V prog. There's the V PRG. That's the programming pin. We talk about that, goes straight over to the Arduino. There's the X latch pin that goes straight over to the Arduino. There's the serial input pin that goes over to the Arduino. On the first one, the serial input goes right over to the Arduino. And then on the second, then there's also the S out pin, which goes to the S in of the second device. Okay, that's how you daisy chain these things together. S clock, that goes straight over the Arduino. We're going to use the SPI port for that. S out blank, the grayscale clock pin we talked about, that's that 8 megahertz, and then all the outputs. And we're not using the X error or the LED open wire pins or any of that crap, so we're going to leave all that open. Now, alright, who's still with me? Let's see a comment if you're still with me, because this is going to be a long video, so I'd be actually kind of curious to know how many people are actually watching this. So anyway, here's the code, and before we get into it, I just want to make a quick little disclaimer. So we're going to be manipulating the timers of the Arduino, which is going to have an effect on some of the other functions that you might be used to. Like, for example, if you're trying to use the existing PWM, like if you use the analog write command in here to write, an analog value and do some PWM on the Arduino, it might not work properly. Or if you're trying to do the tone out, or let's see, what else is there? I think maybe shift out might even not work. So I haven't fully tested this out with those functions. I don't know what I actually, broke while doing this, but it does work beautifully with the TLC5940. So for what it is, it does work, and you might even be able to modify this code a little bit so that some of those other functions still work. Like even delay and delay microseconds, I'm not even sure if those work completely right, because I'm changing pre-scalar values with some of the timers. I don't know how the Arduino sets those up, and since I'm configuring those things, they might not work completely right. Okay, so anyways, let's just jump right into this code. Alright, so first thing right at the top, we include the SPI library. Okay, we're going to be using the SPI ports for writing data to the TLC5940. More on that later. Whole bunch of variables here. We might jump back up to the top and talk more about these in detail. You're going to notice something nice in this code is that I actually have comments. And the reason for that is because this is a somewhat complicated chip to deal with, and I've been working on it for weeks, and So every time I revisit this, I have no idea what's going on in the code. And if I break something in the code, you know, it's how do you figure out what you did? And that's also why I rev the code every time I do a save as, every time I touch it. So like every day, time I revisit this, just so in case I do change something and it doesn't work completely, I can at least revert back. Okay, so anyway, let's see where we're at here. So we set up variables right into the setup here, and we're going to go through the pins now. Everything is an output. We don't read any data from the TLC5940. It does allow that, but we're not doing it. Okay, so let's see here. I do just want to pull open the data sheet. Okay, this is the data sheet for the 5940, which is actually pretty good. I'm impressed. We go right to the pinout here, wherever that is. Okay, here we go. This is the device we have, the 28 pin. And it does go through each one of these pins here in the data sheet and explains what it does, but I'll just go through it here. So we have the X latch pin, and we'll talk more about that later, but for now it's just right on digital pin 2 of the Arduino, and that jumps right over to, I have 2 of these devices, remember, so it just goes right over to the first one and the second one. So you make a wire from the Arduino to this and to the second one. Okay, what else do we got? The OS2B. This is also the GS. Let me just update that real quick. It's also the GS clock. The reason I'm calling it the OS2B is because that is the pin that we're oscillating at 8 megahertz using timer 2. Okay, and we'll talk all about that in a second, but that would go right to GS clock, and that goes to both of them as well, both chips. Or if you had like 10 of these things hooked up, it would go to all of them. Okay, vprogram, we're going to talk more about. Again, that goes to both of them, and I think it's called vprog. Yeah, vprogram. We have the MOSI data and SPI clock. This is the MOSI data, that's master out, slave in. That's the SPI output. You can only use pin 11 for this, or digital pin 11, and that would go right to S in of the first device, and then and then it ends there. And then what you do is you connect S out from the first device to S in of the second device, okay? So the data just kind of goes through one to the second one. It's kind of nice. And then the SPI clock, so that's pretty straightforward. That is your S clock pin right here, and that goes to both of them as well. Well, not as well, okay? Data only goes into one and then shoots out and goes to the next one, but the clock pin is just like the other pins I talked about, which goes to both. Okay, so there's one pin I forgot to talk about that I do work with, and that's the blank pin, and we'll talk more about that here in a little bit. vprogram pin, let me just go through these, make sure ground VC, that's obvious. iRef, this is that pin where you connect a resistor from the pin to ground to set the current limit. In our case, we use a 2K to limit it around 20 milliamps. DC program, I didn't talk about that pin. I just connected it high, so we're just talking, and you can look through this data sheet and see what it tells you what that pin does, but we tied it high, so we're talking directly to the registers. GS clock, we talked about. S out, we talked about. X error we're not using, so I just left that one floating. I believe that's what I did. Yeah, I just left it floating, and then all your output pins. Okay, so let's go back here. Okay, then we set up the SPI. Okay, bit order, most significant bit first. That's in the data sheet. You can go down to the, and we're going to be practically living and breathing this clock, this diagram here, the timing chart. Actually, there's 2. This is the one I want to talk about here. So yeah, here's a great diagram that shows the S in of the first device and then S out to S in. And then all the other pins are the same for both. Everything's connected in parallel. Okay, so here's the timing chart, and it looks kind of confusing, but it's not so bad. S data, so it's showing you that everything is most significant bit. It's not only most significant bit, but the way I found it, it's also most significant channel as well. I believe that's true. You can kind of experiment with this a little bit to find out, like, you know what I mean? Like, so make sure you're talking to, when you send the first 12 bits out the channel, is that controlling the first channel or is it controlling the last channel? I actually can't remember from this code, but we'll get into that here in a sec. I'm pretty sure it's most significant channel, so that's the first byte or 12 bits you would send out. All right, SPI dot set data mode. This is the mode, like you know, if you have a, do you want a 1 to be from a rising clock edge when the data's high, or a falling clock edge? So that's what I set up here, and I think there's some timing diagrams that go into what all that is, but basically I'm using it so it's the rising edge of data, and keep the clock pin low when it's idle. Okay. And then we set up the clock divider, and this is the beautiful thing about SPI. You can actually clock data into something. I mean, that's what you're doing at a multiple of your clock frequency. So we have a crystal that's 16 megahertz connected to the Arduino, and we can divide it down by, in our case, 4 here to clock data at 4 megahertz. Okay, so that's pretty cool. You can go as low as 2, so then you could clock data at 8 megahertz, but when I did that, I was getting some weird flickering and some goofy things going on. I think it's signal integrity related. But anyway, let's keep going on. Transfer byte here, this is going to be the bytes that we're sending out for like the duty cycle information, so the 12 bits information. And these values, the reason I picked 48 and things like that, it's going to make more sense here in a second. And then there's DC value, the dot correction value. So what dot correction basically is, and this is kind of a cool thing about it, the chip is like if you have an RGB LED, the blue LEDs inside are let me start over. So you have with an RGB LED, and if you're writing a value to the blue part of that LED, it's going to always dominate the red and green. That's just the nature of the blue LED, at least on the device I have. They're just brighter, so they dominate them. So what the dot correction allows you to do is fine-tune what the brightness of the LEDs essentially. I mean, you can sort of limit how much current or duty cycle you're putting on that pin, or so it's kind of nice. So each channel of the chip gets a dot correction value. It's a 6-bit value, so 63 would be in decimal would be the max value for a 6-bit number. And so what I do, I just go through all 32 channels and give it 63. Okay, so you can fine tune it, you do whatever you want for that, but I do 63, and we'll get into the dot correction right sequence here in a second. We set up the serial port here. I don't know, I don't use it, but could be helpful for debugging. And then the dot correction right is actually in a subroutine. So let's jump down here. Here it is, dot correction. The first thing we do is write the V program pin to high, and that puts it in so that when you're writing data to the chip, it's writing it to the DC registers, dot correction registers, instead of grayscale. The grayscale registers are for writing the duty cycle to the chip. So first we write the dot correction stuff. You might notice something kind of goofy. I'm not using a standard digital write pin 4 high like you might see. And the reason for that is because that instruction is so slow in the Arduino. It's a lot easier or a lot faster to just manipulate the port directly using like a native language, like this. And you might have to pull open the datasheet to fully comprehend this here. So let me pull open this is the Arduino, or not the Arduino, the ATmega 328 datasheet. This is if you just Google ATmega 328, you can find this datasheet. This is the chip that's used for all the Arduinos, essentially. And it starts, when you look at the chip, you might need to go on Arduino and see what these pins represent as far as like digital pins and analog pins, things like that. But basically, this is your reset pin. This is 0, 1, 2, 3, 4, and then 5, 6, 7, 8, 9, 10, 11, 12, 13. But we're talking about pin 4, which would actually be this pin here. And it's port D, pin 4. So what we do is we go port D, and then we do a bitwise OR with port D with a 1 at position 4. So we're ORing pin 4 with a 1, and we get 1. So we're writing a 1 to pin 4, essentially. Okay, so anyways, we write it high because that's what the data sheet tells us to do when you're writing. See right here, you can see DC, V program pin is high. Okay, we write it high, and then this whole part of the code here is confusing as all hell. This is where okay, so the SPI port can only write bytes. That's 8-bit numbers, but each channel gets a 6-bit number for dot correction. So how do we write, and we have to send these continuously. So if we just sent a 63, like just a 63 and sent, let's just say 32 63s in a byte, well, there's 2 extra bits that would screw up the data transfer. So, you would send your 63, which would be like 6 ones in a row, and then, well, actually it would be 0 0 and then 6 ones, because you do have 2 extra bits at the top of a byte, and that would throw off the whole data stream because it's expecting it to be 6 bits for channel, for the channels. So you send 6 bits, 6 bits, 6 bits. So what this does is it fills up all the bytes so that it's continuously 6 bits, 6 bits, 6 bits. Even though, you're sending a byte, it's going to carry information from one channel and a little bit from another channel. Okay, if that makes sense. So the top 6 bits of the first byte would be for channel, 32, or I'm sorry, channel 31, because it starts at 0. Okay, so that's basically what we're doing, and we do the same thing for the grayscale data, because that is in 12 bits. So when we're sending 12 bits, the first byte we send over carries a little bit of the data for the first channel, and then we have to send a second byte with a little bit of data from the first channel as well. Okay, let me think about that. Yeah, because we can't send 12 bits in a byte. Okay, if it helps, you might want to work through these for loops, and it might make more sense. I don't know. I might need to redo some of this commenting here. But anyways, all right, let's go through this. All right, so we said we have SPI byte and SPI bit. This is the data we're sending out. And then we have channel bit and channel. We have the channel and we have the channel bit. Okay, so there's 6 bits per channel and there's 32 channels. So we go through this channel by channel, and then we go through it bit by bit within the channel. And what we're doing here, skip this part for a second, is we're checking the DC value that's coming down here that we set up, and this can be 63 of the channel, and we're going through it bit by bit, 0 to 6, 0 to 5, 6 bits. And then we're setting the bits and clearing the bits of the transfer byte, which is what we're actually going to send to the device of the SPI byte, which is set up as 0. So it starts at 0, right? And then fills up the SPI bytes. Okay, so it's going to fill these up, and then it increments up the SPI bit number. Okay, so it goes through 6 times, right? But the SPI, we still have 2 more bits left in the transfer byte for this byte, if that makes sense. Okay, so we go through it, we fill up the first 6 bits, and now we have 2 more bits left. So this increments, the channel bit increments up to the next value of 1, and then we fill up the next 2 bits within the SPI bit for the data in the channel. Okay, and then as soon as we overflow that, now we're at the max of the byte. So SPI bit is equal to 8 now. So we increment the SPI byte. So go to the next byte now and start filling that data up, and then reset the bit count. Okay, so we fill up a whole byte with information, then we fill up the next byte with information, and then we get a whole crap ton of bytes. And then now we can send that out. So we do an SPI.begin, and for j is equal to SPI byte, because whatever we maxed out here, we were incrementing the byte count. So as long as we go for j, we start there because it's most significant channel first. That's what we send out. So we start at the highest byte, and then we bring ourselves down. So we send out, the highest byte, then the second highest byte. So we're sending out channel 31's data first, and then working our way down. Okay. I hope that makes sense. That is such a crazy, complicated thing to kind of wrap your head around, and it's going to get even more complicated when we convert 12 bits into bytes. You know, we got 32 12-bit numbers for the duty cycle of each channel, and we have to send that in bytes. So we have to convert it all into bytes. All right, so then what we do here is, now you're going to see a lot of this port D manipulation. I manipulate the port using these direct commands like this, okay? Okay, so then we write the latch pin high, and you can actually see this here. So it says here, you know, you've got your DC value while the V program pin is high, and then you bring the latch pin high for a little bit, and then low. Let me go back to our code here. So the latch pin goes high, then the latch pin goes low. This is the same thing. Now we're doing like a bitwise AND with a 0 at position 2 to bring that pin low. So it goes high, then low, and then we can bring the V program pin low. Okay. I didn't want that. Oh crap, what the heck is this? Try to figure, okay. Then we can bring the V program pin low as soon as we latch the data in. And now we're in grayscale data input mode. So now we can write the PWM values to the channels. Okay. So let's go back to our code. So then that's the end of writing the dot correction values. Coming back up, here we are. All right, now we're gonna get into some meat here. So what we got to do here is we disable interrupts because we're gonna use the timers we're gonna use the interrupts caused by timers and counters in the Arduino to write certain pins high and low and to clock data in, and this is how we're going to measure that we've got 512 microseconds width. Okay, so actually what's nice here is that I've went through and documented all of these timers and what I did. So these are the timer registers. This is timer 2 register. You're going to have to go in the data sheet for some of these things though. And I'll just go through one. So you go down to timer 2 here. Just want to get to show you guys how I'm setting up these registers, and hopefully it'll make sense. Now timer 2 is the one I'm using to oscillate the grayscale pin. I'm just looking here. Now this is all garbage. Okay, I'm just looking for these registers. Yeah. This is the one. How do I close this? Content only. Okay. Okay, so yeah, basically what I'm doing here is setting up timer 2, and then you can set the frequency here, and then up here you can set as to which pin you want it to oscillate. So you actually have two oscillators where each timer is given two oscillators, A and B. So timer 2B is what we're going to be using. I just want to go back to my code real quick and I'll show you that. So if what we have it set up for is compare mode, toggling pin 5 at 8 megahertz. That's pin 5. It's not digital pin 5 like you know it in the Arduino. Let me show you. I think I even have that explained here. So it's digital pin 3. You know, we set that pin for pin mode output on digital pin 3. And we're going to toggle it at 8 megahertz. And then that's basically what this does. So 0101 means toggle pin, toggle that pin timer oscillator B, I guess you could call it. And then right here, this data is these WG. God, I keep clicking the wrong one. Oh, I gotta do this. Okay, and then down below here we have this WGM 20 and 21. This is what sets up the mode. So yeah, here you can see 2A1 and 2A0, 2B1, 2B0, and this is how you set it up. And we want to toggle. So we left, you know, the oscillator A we don't need to do anything with, so we left those at 0, and then we set up B to do a 0, 1, which is, oh, not that one, I meant sorry, 2A 0 toggle, keep going. I have to go all the way down here. So we're in compare match mode, and it's going to be 0 1 on that, and that's what we have set up here. So I'm just kind of working through this. I might make a whole video about timers and stuff. So we set this to 0 1, and now I'm going to do something I'm going to regret, but that is to show you the pin. So I don't even know, just because it's hard to kind of work through these giant things, but I want to show you. See this right there, OS2B, that's digital pin 3 in the Arduino, but it's actually, you know, pin 5 on the chip. But that is the pin we're setting up to toggle. So you see you have OS2B. Why did I choose OS2B? Because OS2A is over here. I could have also used that. But look, OS2A is also the MOSI pin, master out, slave in. So that's my data pin. So I couldn't use that. That's why I had to use B. Okay. I could get back down here real quick. Content only. And this kind of breaks down all the modes, and it's confusing as all hell. Okay. And then you finally, this thing will tell you what to set those WGM values to, these wave generation mode values. And we're using CTC here. So that's the clear timer on compare match mode. The top is this value OCRA and blah blah blah, but we set it up for 0 1, and WGM 0 and 1 are part of the register on A. I gotta get back here to show you my code right there. So we use that one right there. That sets it up for compare match mode. Timer or the register 2B for timer 2B. See, there's actually, I am like the worst here at juggling documents. Then there's this timer control register B. It's just an extension of that other register I was showing you. But see, you have WGM 22 on there. That would have been the high part here of whatever you needed to set, if you needed to set something. But you also have these CS20 values, and this 21, 22, blah blah blah. And the only thing you need to look at is that sets the prescaler value. So like you can divide the clock down, and you can figure out how you want it to count, at what frequency you want it to count at. I'm not going to use any prescaling, so I'm going to set CS20 to 1, which if we go over here, we set that to a 1 right there. And then these other things I could care less about. Okay, let me bring this guy back, and I just want to show you that. See, so I'm explaining this right here. So timer 2 prescaler is set to 1, so we get 16 megahertz. But remember, what we're doing is actually toggling the pin. So you get 1 on one cycle of the count, you're turning it high. On the other cycle, you're getting it low. So you're actually not clocking it at 16 megahertz. You're actually getting a frequency of 8 megahertz on that pin. And that's the max you can get. You can't go any higher than that. The TLC5940, though, can be clocked up to like 30 megahertz. So you can do this thing fast. But we're only working with it at 8 megahertz. All right, then we use, what we're doing here now is timer 1 is the timer that we're going to use to measure the 512 microseconds. Okay, let me show you why we have to do that. Okay, so we're right here now. Now we're ready to start clocking data in. And then you can see this gray, well actually technically we would be right here. But see, we count these 4,096 pulses here off the GS clock pin. Okay, we can clock all our data in, but at the end of this stream, remember this is what's matching the outputs. So if you have these different values for the outputs, it's keeping it high until you get a match with the channel value and what the count value is on the GS clock. So it counts all the way up, and then as soon as it counts all the way up, you have to bring the blank pin high. Okay, that's what you do with it, because the blank pin will actually reset the counter for you. It doesn't automatically reset. You have to do this what you do is you bring the blank pin high, and you also bring the latch pin high so that you're latching in the data that you just sent it during the whole cycle there. So during that 512 microseconds, you're actually sending data to the chip, clocking it in while it's doing its thing with the PWM. And then at the end of the cycle, you bring this latch pin high and you clock in all that data. And then the next cycle it starts over here is using that new data. Okay? So we already discussed that this is at 8 megahertz. And for an 8 megahertz to get 4,096 cycles, we need to measure 512 microseconds. And that would give us 4096. So we use timer 1 for that. And we're not toggling any pins at all. What we're doing with timer 1 is calling an interrupt when we get 512 microseconds. So that first register doesn't need to be set up for anything. It's not the same register that we just talked about, though. It's timer 1's register. So you have to go back to the data sheet, table of contents, and you have to now go to timer 1. It's a 16-bit timer, so it counts way up there, like 65,000 or something if you need to. Okay, we're gonna go all the way down to where it talks about these registers, wherever the heck they are, and we're using clear timer on compare match mode again. That'll make more sense here in a sec. Okay, blah, 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 blah. Here we go. Okay, so we have this timer control register A. You got the waveform generation mode bits here and the toggle pin bits here. So again, timer 1 has an OS1A and an OS1B. We're not using either of them, so we're going to leave them all to 0. And that's what we do here. So that whole register is set up to zeros. The WGM bits don't need to be set on the timer 1A control register, so leave that alone. Okay, then in timer control register B, this is where we set the control or the prescaler, and where we set the mode. The mode is set. I'll just bring it up real quick. Wasn't gonna get into this kind of detail, but whatever. Guess I will. Okay, so we're here. Clear timer on compare match mode. And so we need to set WGM12 high. Here's WGM12 of the timer control register B. And then here's your prescaler values. And you come down here and set your prescaler to whatever you want. In our case, we're going to be using 100,256. Why? You'll see. So there's the one to set the mode, and then there's the one to set the prescaler to 256. Okay, so here's what we got to do. When we get a match on the counter starts at 0, and since we're dividing it by 256, we have 16 megahertz divided by 256. So we're actually making a count at 62.5 kilohertz. Okay, and this kind of breaks this down. So this counter counts up. It starts at 0 and it counts up, and we get a count. I don't know if I have that here, but anyways, when we get a match on the OCR1A register, which is 31, I set it to 31. It will initiate an interrupt. And we'll get to that here in a second. It'll go to like a little subroutine that it can execute some code. So we need that interrupt to execute every 512 microseconds. So what we've done here is done a little bit of trickery. So this breaks it down. So 16 megahertz. We're getting a count 62.5. We need a match at 512 microseconds. So timer 2 is running at, we talk about this, so 512 microseconds, blah, blah, blah. Timer 1 will make a count every 16 microseconds. So at 62.5 kilohertz, we get a count every 16. So we need to find out what 512 divided by 16 is. Yeah, and I think I even have that somewhere here. But 512, it should be, I'm just hoping it is. That gives us 32. So I need 32 clock cycles. 32 counts from timer 1 to get 512 microseconds. So it starts at 0, so that gives 16 microseconds right there. So we'll count up to 31, and the interrupt will execute. And then that's when we could bring our blank pin high. That's when we could bring our latch pin high. That's even when we can start sending data to the chip too. Okay, hopefully you guys are staying with me. Here's the mask register. What this does, this mask deal, is here it talks about the values, some other registers you can play with. The mask register. This is the interrupt. So like, when you get that match, that compare match to A, you want it to go to this interrupt A. So you put a bit in for the mask there, so you want to use A. So you're kind of just enabling it so that the interrupt actually works for you, okay? And we'll get more to the interrupt here in a second. So yeah, we set the one up for A. We're going to use it. We set the value that we're going to match on at 31, and now we can kick off the interrupts, or the timers, which will also work with the interrupts. Okay. Now, let's go over to the interrupts. Here's all the interrupts right here. Interrupt, they're called ISRs, interrupt service routines. So you have 3 here listed for timer 1. For some reason, you need the this is the over limit flag timer, I guess. So like, I don't know. Don't worry about it, but you need to put it in here. And then the compare on B interrupt, you could have a value for B and trigger an interrupt when it hits B as well. But we're going to use it, again, like when we have a match on A. So every 512 microseconds, this is going to happen. It's going to come here and do these things. And look, it does exactly what we said. Write the blank pin high, write the latch pin high, write the latch pin low, and then write the blank pin low. Okay? End of the SPI. And then write the SPI clock pin high and then low. The reason for that, okay, so anyways, let's just go back to I'm trying to get back here, but for some reason, I can't get, no, not you, this guy, yeah. So what I'm getting at, though, is right here is, see, you write this blank pin high, you write the latch pin high, and then low, and then blank pin low. But if you notice here, this is the clock pin for the serial data. There's 193, so it needs an extra clock pulse for whatever reason before you can start clocking in data normally. You're not clocking any data in here necessarily. It's just for whatever reason that clock needs to be high. I don't know. I tried working with it both ways, but I just followed the data sheet blindly and did that. And it works fine, so I do that. Give it that extra clock pulse here. Then we begin the SPI, and then for sign data is equal to 47, greater than 0, sign data less than, or subtract it down. And then we send out our bytes. Okay, 47, that's because we have two devices, 16 channels apiece. Each channel gets 12 bits of data, so 12 bits times 32 gives us 384 bits total. That total divided by 8 bytes, or bytes, sorry, divided by 8 bits will give us how many bytes we need. What the heck's happening here? So we get 48, essentially. That's what I'm getting at. So we need to send 48 bytes to send 16 channels worth of 12-bit data apiece. All right, and that's how the whole thing works. But there's more. Okay, where are we at? Right here, where we set up so we set up the timer, we kick off the interrupts, and then I have a subroutine here called TLC. That's just for the TLC5940. This is how you write data to it. This is how I set it up. So you have 2 values that you write to the routine. First is the channel, the second is the value. So if you wanted to send, if you wanted to make channel 1, 100%, you would send a 1, TLC 1, comma, 4095. And you would get 100% on channel 1, output 1 of the device. Okay. Then what we do, so I went through and I cleared out everything, made sure every output is 0. Then what I do finally is set the pin mode of our blank pin to an output. So up until now, that pin was sitting in a high impedance state. And I do that just so the whole time while we're doing all this whole setup, the LEDs are off. There's no chance of them flickering on or, doing something random. So we do that at the very last second so that now the pin is an output and we can manipulate it. Okay, so let's move on. Now we go into our loop, and I've given you some animations here to play with. You can make them all red, they can make them all green, all blue, and these are the value you want the red, the green, the blue to go up to. There's a lamp test that goes through each LED and goes for RGB, and then there's the random animation. There, I'm just gonna upload that right now. I'm not going to get into exactly how these animations, I'm not going to walk through that. It'll take forever. But here's the lamp test subroutine. So it just works through the channels, and then for each channel, it writes a value from 0 to 4096. So you see the channel starts at 1 and it goes all the way up to 32. And then it writes for each channel a value from 0 to 4096, and it counts all the way up. Okay. Then what it does is it counts all the way down. So it turns it all the way on, then all the way off, and then goes to the next channel. And it just keeps doing that over and over again. This is the all red, the all blue, the all green. Because on my setup here, the way I have it wired is I skipped channel 0. I should point that out. There is no channel 0 on my circuit here. So the first LED is connected to channel 1, which is the red pin. And then channel 2 is the blue pin, and channel 3 is the green pin, and then it repeats, for all 10 LEDs. That's why we have K plus 1, see how it starts at 2 here, and then counts up L plus 3, and then L is 1, L is 3, L plus 3. So yeah, that's how it controls all the red ones. It's every 2, or every other 3 pins, I guess. I've been doing this video for too long. I'm getting worn out. Okay, here's the random. This is the random animation, and it goes through and sweeps back and forth. This is really cool. And it's very simple, but it's like it remembers what the old value was, and then it changes its speed. It's just really cool. I'm not going to go through this, but it's very simple. It's just very trivial. You have to work through it, and it'll give you a headache if you try to figure it out. But anyways. Like I said before, you write these values down to TLC, and there's two values that you write with it: the channel value, and then the value itself from 0 to 4095. This update here, is what really I was stuck on this probably for the most part of when I was working on this project, because the process of updating the values that you're sending out needs to occur very quickly, and this still is pretty slow. This still takes like 1 to 2 milliseconds. So it's not the fastest thing in the world, but anyways, it comes into here and it checks the value, makes sure that it's within range. If it's something, if you accidentally write the wrong value, it'll catch it here and just, give it a ceiling of 4095 and a floor of 0. Okay, then we go through. Now, remember all that talk we just did with the dot correction? Well, we got to do that again. This time, though, oh God, I forgot I did all this. So we have all these bytes that we send out, and those bytes all contain the 12 bits for each channel. But instead of when we come down here to update all of the bytes, what this does is it finds out exactly where in those bytes the 12 bits are for that channel. So it actually comes in here, sets the SPI bit to 0, and if it reads the channel value, it's checking at position 0 to see if it's odd or even, because you got to think about 12 bits. So you have 12 bits, you're going to either be starting at 0 on the byte, or you're going to be starting at 4, because it's 12 bits. It's 8 plus 4, right? So it's either going to be starting at 4, and that's what we're doing. We're doing an odd check to see if it's an even or odd. If it is odd, that means the first bit in the channel would be 1, right? So that means the SPI bit starts at 4. It's kind of complicated, but it speeds things up because now it knows where to start. And then we do this little math here, 12 bits divided by 8 bits, and then I simplified it. This tells us which byte we're starting at, so we don't have to go through each byte to find out where it is. And this is all about speed. We're trying to make this happen as fast as possible. And then it goes through each channel bit that we wrote to it, and also increments the SPI bit as well. And then again, it checks it. As soon as it hits 8, it rolls up to the next byte, resets the bit. And it's checking if bit read value and channel bit is 1, then set it there. If it's not, clear it, and it just keeps going and going. So all this crap up here is just so that we know where to start with the SPI bit and the SPI byte. Okay? I hope that's not too confusing. But it works beautifully. And it runs through the animations. One thing now. Yeah, okay, this is a little confusing. But one thing, if you really need to speed this puppy up, you can get rid of the bottom 4 bytes of your 12 bits. You know, when you're sending these, you know, you got a value from 0 to 4096. Well, if you just chop the bottom 4 bits off and make it, you know, whenever the value's lower than 4 bits, just slam it to 0, then you could just send out 32 bytes, if that makes sense. So instead of converting 12 bits to bytes, to a string of bytes, you could just chop the bottom 4 bits off of each 12-bit value. I might do that, actually, just to see how much faster I can make that. That way you could send the bytes directly to the chip, and you'll lose some resolution, though, so you wouldn't be able to write. I mean, 4 bits, what's the max of 4 bits could be? 16? So, and that's hardly anything. So if you chop that off, but it's kind of nice though, because I like fading things on from 0 on. So if we chop the bottom 4, then we couldn't really fade things on. It would immediately turn on at 16, a value of 16. But if you think about what 16 is in, 4096, when 4096 is 100%, what the heck is 16? It's hardly anything. So maybe not noticeable. But anyway, that is this video. I hope that helps. This will be on the website, link in the description. Hopefully this makes sense, and I hope to see some video responses with people working with these chips, because they're really cool, man. So we'll see what happens next. There might be, I'm thinking about getting some analog circuitry on this board, get a microphone, get it working with some music maybe. Or other things too, like motion sensors or whatever, make it more interactive. I'm also thinking about doing like mood displays with it, maybe even have a temperature input to this thing, so it's like kind of changes its feeling based on temperature and humidity or whatever, I don't know. So, okay, that is the video on the TLC5940. Thanks for watching.